Hello everyone. My name is Biresh and today I will be presenting our work called NoC-enabled 3D heterogeneous many-core systems for big data applications. So in this work, I'm going to talk about why designing a good network on chip is important for a heterogeneous many-core system. So this is going to be the outline of the presentation. So I will first start with a brief introduction on what is a heterogeneous many-core system, and then I will present two examples of heterogeneous systems. The first one will be a CPU GPU based architecture, and the second one will be a ReRAM GPU based heterogeneous system. In both cases, I will present what are the design challenges, particularly what are the challenges in communication, and how we can design the network on chip, and finally I'll show some results in both cases. And finally, I will conclude and present some future research directions. So what is a heterogeneous many-core system? So a heterogeneous many-core system is a architecture which has different types of cores. For instance, here I am showing an example heterogeneous system which has CPU, GPU, audio video accelerator, some custom accelerator which could be like neural processing unit, so on. And because this architecture has a variety of computing elements, this is a heterogeneous system. However, heterogeneity need not be only in computing, it can be in communication as well. We could have a architecture which has planar wires, vertical links, maybe wireless or optical interconnect. So there could be heterogeneity in communication as well. And heterogeneous many-core systems tend to achieve much better power and performance compared to the traditional homogeneous many-core systems. And which is why these architectures are quite popular and are being used nowadays. For instance, Apple's M1 chip is a heterogeneous many-core system. So next, I am going to present one heterogeneous many-core system which uses CPU and GPUs. So here we are showing what a CPU GPU based heterogeneous system may look like. And as you can see in this figure, the CPU and GPU tiles will have a private L1 cache, and they will be connected to a router which will enable them to communicate amongst themselves. And we also have some LLC tile. LLC stands for last level cache. So these tiles will have the L2 cache and the memory controller that connects to the DRAM. And again, the CPU GPU based heterogeneous systems are already being used, like the Apple M1 chip uses CPU, GPU and neural processing unit, and these designs are used in MacBooks. Now here we are going to look into a 3D CPU GPU based design. Why 3D? Because we know that 3D has many advantages. 3D enables higher throughput, lower latency, energy efficiency and smaller designs compared to traditional 2D systems. So here we are going to look into how to design a 3D CPU GPU based heterogeneous system. Now, what is the challenge in designing these architectures, particularly from the point of communication? So here our investigation shows that the communication is quite interesting in these architectures. So here we show a heat map of what the traffic pattern look like between the different tiles. And we see this many to few to many kind of a traffic. So in these architectures, typically the CPU and GPU are the majority. So there are most of the tiles which are CPU and GPU, but very few tiles which are the LLC tiles. But as you can see in this heat map, most of the time the communication is concentrated between the CPU to LLC or GPU to LLC or vice versa. There is very little communication between CPU to CPU or LLC to LLC or GPU to GPU. So we can clearly see that not every pair of core is communicating equally. And this results in this interesting many to few traffic where many CPU and GPU are communicating with the few LLCs. And here we are showing 4 different applications. So each column represents a application. And for most of the applications, we can see that the LLCs are related to at least 90% of the traffic. So clearly this is a problem because this will lead to a traffic jam on chip. So clearly we want to avoid that because that can lead to performance bottlenecks. And apart from communication, there are of course other challenges in designing a 3D CPU GPU based heterogeneous system. For instance, one of the challenge we identified is the problem of high temperature. So typically in a 3D system, we have one layer of cores which is stacked on top of another layer of cores, and in between we have a bonding material which acts like a glue. And here in the table we are showing what is the thermal conductivity and what material is used for these different parts. And as you can see, for the substrate we use silicon and it has a good thermal conductivity. And we also have the copper TSVs which have extremely good thermal conductivity, but unfortunately there is the bonding layer which is made up of a material called BCB, and its thermal conductivity is very poor, like several orders of magnitude lower than the copper or silicon. And as a result, it's very difficult for the heat to move to the heat sink. And this can result in very high temperature in 3D systems that also need to be addressed. And this problem is further exacerbated due to the many to few pattern. So because a few tiles are handling most of the traffic, the temperature around these tiles can also be higher. So we definitely want to address this problem. So how to design the 3D Manycore system? So here we are presenting the design problem as a multi-objective optimization problem. So essentially we are given some number of CPU, some number of GPU and some number of LLC tiles and some wires. And our goal is to place these tiles and these wires in a shape of X, Y and Z. So we want to know how to make this many-core system which will optimize for our different objectives. And here we can have multiple objectives like GPU throughput, CPU latency, temperature, and so on. So while designing this architecture, we want to address the problem of communication. We want a design that can handle the many to few to many traffic and has lower temperature while also optimizing for the other requirements like maybe GPU throughput or latency or reliability. So essentially this is how we can design a 3D heterogeneous many-core system. Now for the network on chip, here we use a small world network on chip design. So in a small world network on chip, the idea is to add a few application specific long range links. So this will result in an irregular network on chip, but what we see is that small world network on chip tends to perform much better than traditional network on chip design like mesh or torus. And this usually leads to much better latency and throughput. And so we use a small world network on chip design for our CPU GPU based many-core system. And here we present some results. So here we have designed the CPU GPU based system with 3 different optimization strategies in mind. In the first case, we optimize only for performance. In the second case, we optimize only for temperature. And in the third case, we optimize jointly for both performance and temperature. And here we are showing the performance, which we measure using the execution time and the full system EDP. And here, as expected, we can see that the performance optimized case has the lowest execution time, which is expected. But when we look at the temperature optimized case, we can see the performance is quite bad. And the EDP and execution time is much higher than the performance optimized case, but the joint optimized case tends to find a middle ground and it sacrifices only 2.3% performance. And in this slide, we show the other side of our optimization, which is the temperature improvement. So again, we consider the same 3 strategies. And here we see the opposite trend. Here we can see that the performance optimized has the worst temperature. So essentially we have optimized our architecture for performance so much that it doesn't care about temperature and the temperature is quite high. But for the thermal optimized case, the temperature is the lowest. Whereas for the joint optimized case, we can see that it's almost as good as the thermal optimized case. So compared to the performance optimized, the joint optimized case has 18 degrees Celsius lower temperature. So this shows that by designing a good network on chip and placing the tiles in a proper way, we can improve performance and reduce temperature at the same time. So that was the first example of how we can design a CPU GPU based heterogeneous system. Next, I am going to present a ReRAM GPU based heterogeneous system. Now, what is an ReRAM? So ReRAM stands for Resistive Random Access Memory, and from the name, as you can guess, it is a memory which uses resistors. So essentially we are storing data on a variable resistor. But what is interesting about these devices is that if we arrange them in a crossbar structure and apply voltage, the current that we get can be expressed as the output of a matrix vector multiplication between the conductance matrix and the voltage vector. So essentially these ReRAM memory can be repurposed to do some very simple matrix multiplication operations. And this is why it's also called a processing in memory architecture. And these are perfect for machine learning workloads which tend to be dominated by these matrix vector multiplication. And there have been many prior work that have proposed ReRAM based machine learning accelerator. But we identified some challenges in these architectures which necessitate a heterogeneous system. So typically ReRAM based architectures tend to have a homogeneous design with multiple tiles of ReRAMs, as you can see here. So each tile has some CMOS peripherals like the shift and add, ADC, buffers, and it also has the crossbars. So it's a homogeneous design. But the main weakness of this architecture is it's only good for matrix vector multiplication. It's not good for other things. But a typical CNN has different types of computation. For instance, let's take the normalization layer. The batch normalization layer requires operations like division and square root. None of them are suited for ReRAMs. So it's very difficult to achieve these operations with ReRAMs, which are good for matrix vector multiplication only. So how do we run neural nets on these kind of devices if we cannot support some of the layers? So here we are showing what will happen if we try to train a neural net without the normalization layers. So typically the normalization layers are used to solve the problem of the exploding and vanishing gradients problem. And here we are showing what that means. So on the left hand side, we are showing what the gradient values look like when we train without normalization. And on the right, we are showing what happens to the gradient values when we train with normalization. And as you can clearly see, when we do not use normalization, most of the gradients are very small. Now, if the gradients are very small, they usually get rounded to zero on ReRAM devices which tend to operate at low precision. Whereas on the right hand side, if we see the gradients, they are much higher and they will not get rounded to zero even if we use low precision. And as a result, the case without normalization will fail to train because the gradients have all been rounded to zero. And so we may not be able to train at all without the normalization layers. So clearly we can see that we need the normalization layers to train the big CNNs. But unfortunately, because these layers require division operation and square root operations, we may not be able to use ReRAMs for these purposes. So to address these problems, we propose a heterogeneous system which uses both ReRAM and GPU. So here the idea is to use the ReRAM's capability of doing matrix vector multiplication and also utilize the GPU's capability to do more general purpose computing like division operations and square root to train big and complex neural nets. So essentially this system can now train any kind of neural net. So here the ReRAM's purpose is to do the matrix vector multiplication, which tend to be mostly in the convolution and full connect layers, and the GPUs will be used for doing the normalization, which can provide the division and full precision support. But this also results in some interesting challenges from the perspective of communication. First of all, in a typical CNN, normalization layers are performed just after the convolution operations. So in our architecture, after the ReRAM operations, we need to send all the data to the GPUs. And we know that GPUs are bandwidth bottleneck. So we want to have a network on chip which will be able to supply the data and move the data from the ReRAM to the GPUs fast. And on top of that, in the case of CNNs, the output of one layer can be input to multiple layers. This results in multicast. So essentially one tile will have to send the same data to multiple other tiles, and a multicast unaware network on chip will end up having a traffic hotspot because of repeated unicast. And so we want to address this problem. To address this problem, we have to use a 3D multicast enabled network on chip. Now, why 3D? So here the vertical links can be used to deliver the data from ReRAM to GPU with high throughput, and we can also do a 3D XYZ multicast to reduce the amount of traffic in the network on chip. And the network on chip has to be complemented with a suitable mapping. So depending on how the layers are mapped to the different tiles, the communication can be very different. So to address the problem of communication in these architectures, we have to map the layers properly and then also have a 3D multicast enabled network on chip. And here I'm showing some performance results of our architecture, which we call accurate, and compare it with a traditional GPU based training. So here accurate is our heterogeneous architecture, which has both the ReRAM and the GPU. And as we can see here, the accurate architecture achieves 15x speed up compared to the GPU. Now here, a large part of the speed up is primarily due to the use of the ReRAMs, but what we also ensure in this heterogeneous system is that we can run any kind of machine learning layer, irrespective of what computation there may be, which will result in much better accuracy. And in the process, as we can see, we do not sacrifice speed up as well. It is still much faster than a GPU based training. And the 3D multicast enabled network on chip ensures that there is no performance bottleneck. It ensures that the data moves fast and the performance is the maximum achievable performance that we can get. And finally, to conclude, we have seen that heterogeneous architectures offer much better power performance compared to the traditional homogeneous systems. However, communication can result in performance bottleneck. We have seen that in the case of the CPU-GPU based heterogeneous system, we can have this many to few traffic, which can bottleneck performance by causing a traffic jam on chip. And in the case of the ReRAM GPU based communication, we saw that the traffic is multicast based and it has to have high throughput between the ReRAM and GPU. Now, if our design is not aware of this, we can have suboptimal performance. So we definitely need to address this, and designing a good network on chip is needed to ensure high performance. Now, in the future, there can be many interesting research problems. For instance, we can use machine learning to solve some of these problems. For instance, we can use machine learning to find out the best network on chip possible for a certain architecture and for a certain application. Similarly, we can use emerging technologies for network on chip design. For instance, we can use wireless or photonics interconnects in these architectures to even improve the communication even better than what we have now. And also we can work on the application. So we can design the application in a way that it's more hardware aware, hardware friendly, and it will automatically lead to lower communication. So there are multiple problems that are waiting to be investigated, and hopefully in the future a combination of these will solve the communication bottlenecks. And with this, I would like to end my talk, and thank you, and please let me know if there are questions.